All right, welcome everyone for this OICU ALT seminar series. So today we are very pleased to have Nick Lane to give us a talk about machine learning, federated learning, and many things. So let me give you a brief introduction about Nick. Nick is a stellar researcher. Well, now I think it's more than a researcher now. He's an entrepreneur, and he's also affiliated to Samsung, the company, well known. So Nick is, I think the better title for him is now a part of this is a full professor in the Department of Computer Science and Technology, and a fellow of St. John's College at University of Cambridge, UK. I know Nick for a long time, and he is one of the very best researchers in the field of mobile computing, and actually many areas. And at Cambridge, Nick leads this machine learning system lab alongside his academia appointments. He is also the co-founder and the chief science officer of this Flower Labs. Basically a venture-backed AI company. I think it's a Y Combinator, one of the Y Combinator funded a company this year. Nick has received the multiple best paper awards. Just name a few, including the ACM IPSN at 2017 and 2 best papers from ACM Mobicon. And in 2018 and 2019, he and his co-authors received the ACM Census Test of Time Award and ACM SIG-Mobile Test of Time Award for pioneering research, which is done during his PhD, that devices, machine learning algorithms used today on devices like smartphone, wearables, and IoT devices. Nick is also named as a 2020 ACM SIG-Mobile Rockstar Award winner for his fantastic contributions, cited as the understanding of how resource-constrained mobile devices can robustly understand, reason, and react to complex user behaviors and environments through new paradigms in learning algorithms and system design. So, although short, Nick is, again, one of the very best researchers in this field. And without further ado, let's give the floor to Nick.
Thank you. Thank you so much for the kind introduction and inviting me to be here today. It's a pleasure to be here virtually. What I want to chat to everyone about is about my new passion, which is federated learning and what it means for machine learning and the data center. And so I'll be telling you today my thoughts on where things are headed in terms of machine learning and how I think we might start to view this intersection of machine learning and data centers that we currently have. So just without further ado, let me first just define what I mean by this intersection of machine learning and data centers. And so I'm talking about this current ecosystem that we live in, whereby machine learning is sort of inextricably linked to data centers. And that's because of the type of technology we use in machine learning today. That we have these giant, and they get even larger neural networks. That requires us to use huge data centers. And by extension, this sort of apparatus requires us to carefully curate large amounts of data and put them in these data centers and have everything co-located so we can build these models. And this is an ecosystem that you can't escape. There's no other sort of way to live your life today whereby you can't opt out. There's no way to opt out of this current situation where we have machine learning models being trained with data centers using this carefully created, relatively large scale data. And so because of that is, if you do a search on the web for an image, there are machine learning models trained in this manner driving that search. If you use your phone, there are hundreds of models trained in this manner on that phone. If you use Alexa, if you even go home and you watch Netflix and you the little thumbnails being picked, the codecs being used, everything is even driving that service, right? So you can't escape this apparatus, and I'm going to argue that this apparatus, this intersection of machine learning and data center is much worse than we even really fully realize. And so I'll start off this talk by saying that in a few years' time, it's hard to know how many years, maybe 10, maybe 5, maybe less, we're going to start looking at this machine learning and data center kind of combination and drawing a parallel with that to other things that society has done in the past. So an example of that would be smoking. There was a time in the Western world where smoking was a good thing. Doctors recommended it. People smoked a lot. They didn't realize that they just didn't realize the negative health effects. And I would say that in the future, we'll look at data centers and the sort of ties with machine learning, and then we'll suddenly realize that there are a lot of negative externalities associated with this relationship. And we're going to see it in the same way that we see smoking today. Terrible thing we used to do a lot of, we didn't really understand, or there was another alternative, but we did it anyway. And eventually we evolved to not do it anymore. Another example, lead paint. There was a time when I was a kid in New Zealand, we used to paint, all the walls with lead paint. It was terrible for health, but we didn't have an alternative technology at the right price point that we could use. So we did it. Eventually we learned better. We knew the negative externalities, and we stopped doing it. The environment. This is an example, unfortunately, that we haven't been able to get ourselves out of. So we're still polluting the environment. We're still causing climate change, even though we know that we need to stop this. But what I'm trying to do here with these 3 examples is that this is as bad as we're going to view the data center in time. We're going to say, whoa, there was a lot wrong with machine learning and data centers and the way that we use that for such a long time, because there's a lot of negative externalities that came with that setup. And so let me get rid of this pop-up. Yeah, so why do I feel so strongly that we need to move away from this combination of machine learning and data centers? Well, here's a laundry list of the reasons. I'm going to walk you through it. The first of them is fairly obvious. It's user privacy and control. If you're training these models in the data center, they require you to upload and centralize all of this data. And once you do that, you lose control as a user. There are laws and legislation and regulations emerging in Europe and elsewhere. They're saying you can't do this, or you need to have strong controls over this. But even without those laws and this movement, this is a fundamentally bad situation to be in, because once the data is in that data center, you don't know what some company or some other organization is going to do with it. So that's a bad situation. What else is there? Well, another example would be any system that you build in this manner. So if you're building a robot, if you're building a smart stethoscope, if you're doing any of these things and the brains of that device exist in the data center, that's a big problem, because as soon as the connectivity to that data center go down, you have a dumb device. You've potentially a dangerous device. If I'm a robot and I'm moving around, I suddenly need to react on a very short timescales. And if the latency even drops and my connectivity starts to dwindle, again, I could have a bad situation. There are other situations that make this a bad type of sort of relationship. One that I'd point out is this reliance on static data sets that are carefully curated, things like ImageNet and so on. Well, it's impossible to have, no matter how big these data sets get, if the process is one by which you collect the data, you polish the data, you clean it, and then you centralize it, it's always going to have a pretty big gap between that data, no matter how big it gets, and the real world. Because that real world is just, so much larger, it's so much more dynamic. And one of those problems is that you can't model everything that you're going to see. And so then if you take an example of recognizing faces, we're starting to see repercussions of that relationship. And so some people point to machine learning techniques that are biased, and then point to solutions, technical solutions to overcome that bias. But one fundamental pillar for why those systems are biased is that the underpinning data that they train on is a poor reflection of what reality really is. And so I would say that this relationship of big models being trained in data centers where you have static data is and what is a big source of why we have biased data in machine learning. Another bad problem with this setup is carbon footprints. I'm sure this result is something that you might have seen around because it's been talked about for a number of years now. But if you look at this one anecdotal result on the right-hand side, it's from a paper that talks about state-of-the-art models from a few years ago in the area of NLP. What they point out is that if you want to train an NLP model that's state-of-the-art at that time, and you put on all the bells and whistles, you do AutoML and you do everything else, you end up, for the cost of training that single model, you end up producing the same amount of carbon, or more than, you produce the same amount of carbon as the lifetime carbon footprint of a car in the US, of 5 cars in the US. And so I guess the point here is that carbon emissions of this style of learning are also extreme. And so there's a number of reasons why we would not want to use this technology. It's a number of reasons why I'd argue that it's a bit of a dead end, and we should really start to innovate away from it. And so when you start to think about these things, a logical question is, where are you going to go next? So there are alternatives. What I want to argue for in this talk is that we need to start looking seriously at different forms of decentralized machine learning. That's the core message. But along that way, we have to see what can we use. And so we could start to use on-device machine learning. That answers some of these problems, but not all of them. One of the things it answers is that some of the brittleness to do with the systems relying on data centers, or some of the privacy concerns whereby at least the inference time data gets to stay on the device. And so there's some degree of control. But fundamentally, these models still have to be trained in the cloud, in the data center. And so a number of these issues still remain. There are some interesting, exciting different types of learning out there, some related to self-supervision, some related to zero-shot learning, and so on, that could be used in some way to do sort of local little sort of learning that could replace the data center in different forms. But the big problem is that all these exciting sort of emerging ideas struggle to match the accuracy that we have from this sort of existing approach of data centers and machine learning coming together. And so right now, the most promising direction to kind of invest our intellectual energy in is federated learning. And so while I think generally speaking, the broad direction we should all be headed for is that of some sort of forms of decentralized learning, if you want to start investing your intellectual energy today, it seems that the best place to start is federated learning. And then for those of you who are not very familiar with it, I'll just give you a couple of slides just to kind of ground this discussion. The whole sort of core idea of federated learning is that you want to enable silos. So they could be institutions, they could be individual devices who have data. So you could have a smartphone of a user, has some data on there. You could have a hospital that has a lot of data in there. And rather than asking these silos to send the data to a third place, to a third party, a data center, you ask them to do learning on the data they have available, start to calculate some gradients, compute the losses, figure out how to build a model that improves based on the data that they have available to each other. And you end up with independent views of the problem. Then you'll send those views, those model updates, to one central place and aggregate them together. And so there's a lot of, obviously a lot of details in this space, but that is the kind of core concepts you should be thinking about. So as an alternative to uploading data to a single data center, bringing it all together and having a learning algorithm run over all of that data in one place, it's a push towards techniques that allow learning to occur on the edge or in these silos, to have a lot of the discovery happen locally, and then aggregate those local discoveries, those local evolutions of the model together as a way to build these models. So before I go any further, I do want to also mention that I'm talking mainly today, almost exclusively today, in terms of classification models and conventional types of learning tasks. but it would be quite simple to change a lot of these discussions to describe execution of analytics. So simple queries, different types of aggregate sort of functions running over data to answer data science type questions too. I just want to point that out as a definite direction that you could use. All this discussion could be kind of shaped around too, but for the sake of discussion, we're just talking about classification results. So we've talked about federated learning. I've talked about why I think it's so important for us to get towards more mainstream use of those methods. Let's look at how they're being used today. And I think it's sort of a fascinating situation whereby federated learning simultaneously is a huge success and not really commonplace yet simultaneously. Because the reason is that you can look at a few companies, few big tech companies like Google and Apple, Meta, there's a few number of those folks, and they have collected together enough researchers, invested enough money, overcome enough technical hurdles that they can solve specific federated problems. And so if you use your phone today and you use the keyboard, federated learning is training that keyboard. If you look at the recommendations in Chrome, I believe, the settings of Chrome's recommendations are driven by federated learning. But what's interesting is that outside of these big tech applications of federated learning, there's just a lot of proof of concepts out there and sort of, not really fully baked applications. So there are trials being done in hospitals around the world. There are small proof of concepts with robots where there are wonderful types of, potential things happening, but it's not really being used in mainstream to solve many of the problems that you imagine it could be. And so it's an interesting situation whereby the technology is proven out at a large scale, but it's not really deployed en masse to solve machine learning. I guess the other thing I'd like to say is that it's fascinating to think that despite all the discussion in machine learning today, and how excited we all are, all of it is still being used, all of it is still using centralized learning. So, ChatGPT, AlphaGo, you can't name an innovation in machine learning that was trained in these approaches. So there's a big gap to be filled here. So why is that? Well, there's a lot of hurdles that we still have to overcome. And so what we're really interested in is overcoming enough of these hurdles, and in particular, making it easy enough that data scientists and machine learning folks start to do federated learning without even thinking about it. And so I think the analogous thing you should think of is that we believe that it's important for federated learning to become as easy as it was to do deep learning with these deep learning frameworks like TensorFlow and PyTorch, relative to how it was initially, where you had to do a lot of the work yourself. You had to code a lot of backprop. You had to hack away at CUDA. You had to do so many different things to even train a basic architecture. And then one day these frameworks came along and enabled you to explore a new space, really innovate in powerful areas and have a lot of breakthroughs that were standing on top of simply an enabling framework. And the enabling framework needs to start to overcome quite a few problems. One of these needs to be, there's a huge dependence on using labels and supervision in these systems right now. Almost all the federated learning systems you can find either inherently have labels as part of the application, they just happen to be lucky in that fact, or they assume in the work that labels already existed somehow. Another issue that it faces is because the optimization becomes hugely difficult. If you have these independent views of the data, coming up with a global optimization is inherently hard. You also no longer have the ability to form nicely behaved mini batches that really represent the whole data set in terms of the gradients. That's a really fundamentally hard problem to solve. There's of course system challenges that need to be overcome. It takes they're so much slower to converge, and when they do so, they need to have so much data being exchanged that when you start to see these problems, you start to realize why federated learning, despite all the benefits that it could provide, and despite the amount of urgency that I tried to describe towards moving away from what we have right now, It just hasn't happened yet. And so all of this prompted us a few years ago to develop an open source framework we call Flower. It's a framework in the sense of first and foremost trying to enable ease of federated learning exploration and enabling a community to build on each other's efforts. Because when we looked at a lot of existing federated methods and even kind of underpinning technologies like DP, as a differential privacy and SA segregation, a lot of the, the interdependent parts that are so important, we found that there was a lack of abstractions, a lack of component reuse. And so we wanted to build a framework that could solve a lot of these problems, also provide people with end-to-end development to deployment, and have a lot of the sort of independent, a lot of the problems along the way, such as performing scalable simulations as one, that really act as barriers to people developing, testing thoroughly, and eventually deploying methods of this kind, because it just simply was way too hard compared to data center style learning. And so around Flower, we've built up a very strong community. Flower is completely open source. And then there's a lot of community being built up through things like the Flower Summit to be run annually, or folks simply getting together by themselves to develop the tool. And so this is all basically the key message that I want to deliver in this talk, is that our view is that we need to get there. And the only way for us to get there is by working together. And so while there are some really strong other frameworks out there that are really excel at different parts of the problem, the thing we're trying to solve with Flower in particular is ease of use and community ownership of what we're trying to do. And as you heard earlier, just recently, because Flower has gotten so, basically the community got so large and things are moving so fast, we have had to develop a standalone company to support the open source framework. The framework and everything will always remain open source, but we need to be able to scale up developers to build out features. We need to be able to attend to the community in terms of responding to queries. We need to be able to support so many different devices that people want to deploy on. And so all of that was just far too much for kind of conventional funding, like through governments and through academic routes. And so we've developed a company called Flower Labs that helps support Flower and is trying to get us towards this mission of machine learning that is far more collaborative than that is possible today, far more open, and just inherently where distributed data is sort of a first-class citizen. And so if this sort of interests you, I would point out that we have our next Flower Summit coming up fairly soon, end of May. It's hybrid and in-person. It's in-person, hosted in Cambridge, UK that is, or online if you're interested. And finally, I'm starting to get to a bit of technical content. And I really want to point out that the technical content is all enabled by the folks you see on the right here, who are core contributors to Flower. Most of them are PhD students, some postdocs, but also folks in other walks of life. So people working at Nokia Bell Labs, people working at Samsung, who are interested in this open source sort of movement and want to sort of devote their time, their free time to kind of pushing this forward. So let's look at some of the sort of more interesting technical content now. One problem that we saw in the evolution of where federated learning was going was that people have not really been testing their algorithms under the situations that they are motivated by. And so we saw that people were testing their algorithm, assuming a sort of a pool of clients on the order of 100 or 1,000, and assuming concurrent, clients involved in the round and the orders of 50 or so. And then sort of really only judging the performance under a very narrow setting. And so what we've done with Flower is made it very easy to scale up these simulations so that you can finally start to understand just how well your algorithm will work at scale. And that's sort of a fundamental piece to the equation. If you don't know how well it's going to work when you actually deploy it, you don't know whether you're going the right direction or not. And so there's lots of different components of this kind that I'll point out. I've mentioned that it's easy. We like to say within 2 or 3 lines of code, you can turn a centralized workload that you might have coded in PyTorch or TensorFlow and turn it into a federated one. And so there's just a couple of examples here of doing this. I want to start off by telling you more about Flower in the sense of its scalability and training speed, because we think simulation is one of these key enablers. If you can simulate, as I was mentioning before, if you can simulate at scale and you can simulate quickly, then you can start to really explore the design space properly. And so this first figure that's on the left here, this is Flower training a Distilbert architecture, so a non-trivial architecture. And we think this is one of the few examples of training at a truly large scale. So this is a 15 million client simulation. It's total clients, not clients per round. And you can see that the system is able to converge quite well in different settings depending on how many clients you want. So it's just anecdotal examples of, hey, look, we can scale our infrastructure using academic levels of resources. I think this is using about 4 GPUs to do the simulation. You can scale it well. Another piece of the puzzle isn't just about scaling the number of nodes, it's also scaling the speed of simulation. If it takes me too long to simulate something, I'm never going to be able to explore the design space quickly enough. And so this is a very recent result that's about 2 weeks old, whereby we pushed forward our simulation engine even further, incorporated some new exciting ideas that I'll explain shortly, but we've able to provide simulations at a much faster rate than other types of frameworks. And so FedScale perhaps is a fairly well-known framework these days for scalable simulation. What you're seeing here is different common federated data sets. Shakespeare is doing an NLP task. OpenImage is a fairly large classification task on images. Google Speech, as you would imagine, is doing ASR and hotkey word recognition, that style of speech analysis. And the y-axis here is the throughput of clients in terms of clients per second that are able to be simulated under, I think this is around 2 or 3 conventional HPC GPUs. And so the big takeaway here is that Flower, when combined with this new method that we call Pollen, is able to, perhaps 3x or 5x the speed of these simulations. So, a big enabler, we think, for the community. Yeah, that's what I just talked about, big gap. So what's driving this? It's actually a combination of technologies. One technology we've had for quite a long time, it's called this virtual client engine. The core idea is that we want to intelligently instantiate client resources when they're needed. And so, so you can have huge pools of clients, but you're only really instantiating the ones that you need for the simulation required. So that means that you can scale this up much larger in terms of GPU resources, GPU memory resources, and so on. The other factor here, the real innovation that allows us to get this extra big boost of speed is in the allocation of clients within the GPUs itself. So this is this Pollen method that I mentioned. The heart of Pollen is a predictive model that looks at the total workload of all the different clients, when they need to be simulated, how they need to be arranged, what sort of computation needs to be done, when does various types of aggregation of different inputs need to occur, and it estimates how much resources it's going to take and how long it's going to take based on the potential target GPUs. It does all this and then performs an allocation scheme that tries to optimize the speed. And so, as well as it's able to estimate the execution of these individual client workloads, it's able to accelerate the speed of simulation through more intelligent usage of GPU memory resources and the scheduling of when actual pieces occur. And this is really an important piece because you can't just take off-the-shelf distributed training algorithms that that solve a similar problem, but do so on a completely different sort of problem space. Because distributed GPU problems really face big chunky workloads for training much larger models. Federated learning workloads really have this quality of tiny clients doing tiny bits of work that then at different stages of the simulation need to be aggregated together for the round to occur, for you then to progress as you train the model. So it's a completely different type of space. Just to say a little bit more about Flower that I'm not going to talk about anymore in the talk, is that not only can it scale things up, but it can allow you to do important different types of sensitivity analysis, such as system resources varying and simulated. So you might have your wireless connectivity fluctuating, you might have different amounts of compute in terms of the various types of clients that are participating. It also enables you to do systematic, repeatable comparisons between different types of federated learning algorithms by doing the simulation engine, but you can then, as needed, bring in real devices. So you can have these hybrid types of testing done where you have a mixing of virtual and real devices, such as a phone. And then not only that, we think it's important that once you've developed your algorithm, you've tested it, you think it's great, you've simulated, and you've convinced yourself that it's going to be able to work under the conditions you care about, we want to allow you within the same framework to just deploy it. So it's a fully functional system in terms of being able to deploy a federated system, be it on devices like a phone, or be it in sort of, cross silo setups between different organizations that want to work together. So what I want to do in the rest of this talk is talk about what we've used Flower to do in terms of research and little different types of research insights we've gathered so far. So I'm going to talk about 3 of these at a pretty high level, and hopefully we still have some time to sort of have some questions about where this area is going. The first is the oldest of the pieces of work. It was us looking at using Flower to train a fully end-to-end speech recognition model. And we wanted to look at this problem under much more realistic conditions than we saw it being done in prior works. What we realized is that this problem, where you want to train a speech recognition model, not a hotkey word recognition model, but a fairly open vocabulary model, and you want to train that under federated conditions, we realized that most of the papers were using off-the-shelf data sets that lacked fundamentally the qualities that you would encounter in a federated system. So if you're out there using LibriSpeech, it's not going to cut it. You're not going to see the different types of federated variations that you would encounter in a true federated system, whereby you're imagining people coming together where each person is speaking in a different way. They're collecting their data with different microphones. They're collecting their information under different acoustic environments. And you want to leverage this very highly heterogeneous data to build a much better ASR system through sheer scale of the data. That's where we want to get to. And we realized there was no data set that could help us with that. So the first thing we had to do was to construct this data set. Again, LibriSpeech is not going to cut it. It has nowhere near the qualities I just described because it's a conventional speech recognition labeled data set, right? So it's a relatively small number of speakers speaking in a very homogeneous settings. And so, it's a much easier task to do. And when you just slice it up into different clients, all you're really doing is coming up with some sort of funky type of distributed training. It's not a federated system at all. And so we built a data set based on Mozilla's Common Voice. We used the French language, and then it wasn't hard science, but we just had to manually engineer that data set into a way that it would approximate what you would find in a federated system. That was step number 1. This data set is, fairly large scale. We had a setup where we had 4,000 training users. We had 4,000 test users. And then we wanted to see how well federated learning would work under some of the more recent architectures that perform ASR. And so we set up a sequence-to-sequence model using CTC loss for training a speech recognition model. When we first tried it, it didn't work. So we had to invent a few important sort of hacks in the recipe to make this thing converge. 2 of the conversion necessary pieces, one of which was that we found that we needed to perform a model warm-up. And so what we had to do is we had to hold out a small amount of data that you need to, labeled data that you need to have available centrally. You train the architecture essentially just for a small number of users that would set the parameters to such a state that when we release it and start training in a federated manner, full scale, the thing would actually converge. We also found that at model aggregation stage, conventional aggregation strategies weren't really effective. And so we adapted them so that instead of being weighted on things like how much data does a client have, when aggregation occurs, we aggregate in a manner that is attentive to the word error rate of individual clients. And so we want to basically overweight those clients who are shifting the accuracy up higher than others. And so by introducing these couple of methods into the recipe, we were able to train, let me move one forward. We were able to train a full ASR model under really rich, complex federated learning settings. And so I'll show you one result in this that I want to highlight from the paper, and that was that if you look on the bottom right-hand side, we were able, under both federated device settings, so you have a lot of different clients, you imagine those clients are relatively low resource, or under cross-silo settings where you have bigger clients. There could be different institutions. Each institution has a relatively large amount of data. We're able to use this method to train an ASR system that could approximate what would be sort of your upper bound of performance, where you imagine that you have all the data centrally available. And so you can see that the centralized solution is around 20% word error rate, and our federated approaches are able to approximate that, which is a good initial sort of result. There might be a little audio coming through.
Yeah, I think I mute other people. Nick, can you?
Okay.
Yeah.
Yeah, sure. Okay, so that was a result to do with speech recognition. It showed us that under realistic conditions using FLAIR, we could build a very realistic speech model, and it started to really, I think it provides us an interesting place that others can start to innovate on top of when they try different architectures and so on. The next result I want to tell you about just briefly is that of carbon footprinting. I touched upon this topic earlier. I said that centralized learning had a bit of a carbon footprint problem, to say the least. And so we wanted to ask the question, how does centralized learning compare to federated learning in terms of its carbon footprint? And in particular, we were curious about, can we find some insights, or at least can we develop a methodology that would allow us to change the way federated learning works moving forward so that we could reduce its carbon footprint? There's this old adage that if you can't measure something, you can't improve it. And so we thought it was an important thing to enable us to measure the carbon footprint and allow repeatable measurements of federated learning before we have kind of defined it fully and it's out there in the real world. So again, reminder, ML efficiency is a big environmental crisis in the central land, and we want to study this problem for federated. And so let me just skip this slide, I think. Or let me just say a few things. I think long-term, the carbon potential of federated learning is very interesting. One of these things to observe is that there's no need to cool the compute. And so you have a typical data center PUEs that can be as high as 1.6. That means 60% of the energy is being used to cool the data center rather than power the GPUs. It's also interesting to note that in the long term, federated learning systems probably can reduce the amount of data transmission because instead of in situations where you get a lot of data from the edge. And so if you can, rather than move the data, centrally, but compute on the edge, it's possible that that can have a big positive effect on the energy required for the system to work. So although federated learning hasn't been designed for it to be low carbon, I think there's a lot of interesting properties that it has that means that it potentially can be engineered that way moving forward. Before I show you any results, I just want to sketch out what was the missing piece. The missing piece was developing a carbon footprint model that would allow you to describe different types of federated systems. So, how many nodes, where are those nodes physically located, what type of machine learning workload, what's the data, how long does it take to converge, all these, basically set up the system, and then you import it into the carbon model, and then you can decide how much carbon it's getting. So this step one, this modeling part had to be able to account for the cooling needs of a data center versus the cooling needs that were not needed in a federated system, and needed to be able to account for the fact that in federated systems, a lot of CPUs are going to be used. So they need to be kind of realistic about the type of compute processing that it's doing. Whereas in the data centers, there are GPUs. Data storage and transfer costs between the two different paradigms are completely different. You need to be able to model, in the federated case, examples of using wide area networks, sometimes cellular, or at least links that are working over a long distance. And in the data center, obviously, the storage and the transmission is completely different. It's, very low latency links, and it's negligible different types of terms of the energy. Another interesting fact that needed to be encountered was where are these systems? Because each location has a different profile of how it converts electricity into carbon if you want to do this accurately. And so we use Flower to measure very accurately the things like how long convergence would take, how much compute cycles were required, and so on. And then we plugged it into the secondary carbon model that we had to develop that allowed these comparisons to be possible. So there's a lot of analysis that was produced. I'm not going to tell you, the sort of summary and lots of details about what we found. I just want to give you one result that's kind of interesting, that maybe could spark your interest to read the journal version of the paper. And so that was that we wanted to compare the situation of training a ResNet architecture under CIFAR 10 under a reasonable situation of federated learning, where we had, I think we had about 50 clients, where each client was an Xavier NX. So, this is the type of hardware you might imagine being inside a robot or a very high-end camera, perhaps. 5 clients per round. The target accuracy was 60%. And we compared it to a modest data center, so V100s, a single data center GPU, and we wanted to train these 2 models under a CIFAR 10 model. And then what we found was kind of interesting. In this particular situation, this was a case where federated learning actually had a lower carbon footprint than the data center, which is why I'm still telling you about it. One of the reasons for that is that we found that in certain situations where you had enough local compute, so we imagined that local compute is going to get stronger and stronger and stronger. And so when you had enough local compute, you could start to have trade-offs that look like this. There's actually a different results trade-off, but the trade-off is indicative. And what we saw in some situations, that although the convergence of federated learning was a lot longer, because there's a lot of uphill battles that convergence has to fight because of things like non-ID. Although that you need a lot more epochs and rounds to get there in terms of the level amounts of training accuracy, it could still be lower than its data center counterpart, because the per unit client carbon footprint of the client round was so much lower than the data center's cost. And so you have an example whereby the gradient of carbon emissions as epochs accrue is so much steeper than that of the federated learning. And so there can be many situations where federated learning is actually more carbon footprint smaller. So I think that's one interesting thing we can discuss, but before we move on to the discussion, I want to talk about one final result that I think is really interesting, and that is combining federated learning with self-supervised learning. I mentioned in the earlier part of this talk that up to this point, almost all the federated systems you can think of, if you look inside them, they have strong assumptions about labels. They're assuming an application where labels come for free, like in the case of the keyboard, or examples whereby you just assume that the user or someone is labeling the data, and that limits the applications that you can really build. So we want to look at, how would you build a self-supervised learning system inside of a federated setup? So this is a paper we published in EECV last year, and we designed a method for doing video understanding using self-supervision in a federated system. We call this setup FedVSSL. And let me first just describe the high-level approach of the SSL training. There's basically 2 stages. Stage 1, you want to train a backbone, whereby you set up a series of pretext tasks that can be initialized, and where the ground truth of the task can be computed without human intervention. So an example of this would be rotate the image unnaturally, like maybe you flip it upside down, and you ask the model to predict whether the original is the right way up, or if the one that's upside down is the right way up. And so by presenting a series of tasks to the backbone that solves these relatively simple tasks where the ground truth can be just computed, you can actually train architectures that have quite a bit of understanding about the task. So in the case of video, they can be fairly strong backbones that you can get from free from unsupervised data. The big win is if you can apply it in the case of FL, you can have access to so much more data, and data that just has such a more narrow domain gap between the training data and the test data. And so we developed the system where we did this pre-training of the video backbones in a federated manner, and then we did in a centralized manner the downstream tasks, where you take that backbone, you take that embedding that you've trained, and then you have a small amount of labeled data, and you fine tune it for example, video clip retrieval or action recognition. I'm not going to tell you about the details of this method. You can read that in the paper, but the point is by carefully designing the setup, we could overcome things like communication costs, we could overcome things such as the local compute, and then we could define methods of training in a federated manner, these type of methods that don't require labels, in a way that is competitive or sometimes superior to centralized self-supervision. And so computer vision folks love seeing these little black dots, and that means that their method is a bit ahead of the default one. So this is, the standard CVPR style table. You have this core method that you want to test. You have a centralized version, that's the baseline in the case. And then we have a lot of variations that we developed. And you can see here that the best results, because larger results are stronger results in this particular way of measuring success. You can see that all the black squares are within the range of our Fed v SSL in comparison to either centralized or in comparison to a naive Fed average style federated learning solution. So it's the best of our knowledge, this is the first time that somebody has shown that federated learning can be combined with SSL in the domain of video understanding. So we're pretty excited about the result. And again, this was built on top of Flower. So I see we have about 8 minutes left for conversation. Those 3 techniques have all been built on the framework that I described as being very enabling. So I'm going to leave you just briefly with one prediction, and that prediction is as follows. The rate of evolution of federated learning is such that I believe in 3 years' time, we're going to see our very first example of a federated system outperforming a data center one. And that's going to be a light bulb moment for many people, because right now our world revolves around data centers. Our world revolves around this idea of capturing some data, putting in the data center, cleaning it up, and that's the best way to train a model. But I believe that we're getting very good at edge learning. I think the rate of improvement in terms of efficiency of training models is increasing on the edge, and we're soon going to have example systems, not all systems, but we're going to start to see early examples of systems such as the one I'm illustrating on the left-hand side here. Maybe it's going to be an IoT-based system, for example, doing some computer vision task, whereby the data of that system is primarily coming from the edge. It's primarily data that's captured in the home. It's primarily captured from doorbells. It's primarily captured in kitchens. And that's the source of trained data for the model. And then that type of system will start to outperform anything that someone can build that's data center driven and centered. And that's because we're going to start to see the unfair advantages of federated learning and SSL coming together to create situations where that federated version just dominates alternatives. So an example, what's happening here? The data avalanche that you'll have available from the edge will be unaffordable to send to the cloud. The data you get from the edge is going to have this very much smaller domain shift between the data you're getting and anything you could get with the curated data set. And then it'll have this property of being dynamic and adaptable in an open world context of like whenever the postman, if that postman changes the uniform, if the user changes the look or the visual aesthetics of their home, the system will just adapt. And that'll be a killer feature for such a system. And I think that is probably about 3 years away that we'll start to see the very first signs of that. And this is going to be a watershed moment because we're going to see the beginning of the demise of the data center. And so with that, I'm happy to take questions. I'll skip the last few slides, and I'm looking forward to talking with you all. Thank you.
Thanks so much, Nick. Very nice talk. Well, I think many people are very curious to know why named flower, right? I think that's
Oh, it's a good question. I mean, I guess we wanted to echo sentiments of sort of like a natural environment where things are connected, and you know, there's natural growth, and there's a sort of I guess the main point here is that Earth works when things are in harmony, and right now machine learning is not in harmony. It's just a bunch of rich guys with a few GPUs polluting the environment and really sort of just grabbing data off the web and hoping like hell it works in the real world. And that's not what machine learning can be. Machine learning can be distributed, it can be collaborative, and it can be open.
I also noticed that there, I think on a few slides, you know, you mentioned about Poland. So I think that's kind of like something built on top of Flower. So
yeah, so Poland is this thing we finished just about 2 weeks ago. It's our next generation simulation engine that lets us have those 3 to 5x gains over alternative ways. It's mainly based on prediction. Once we can have a very good prediction of how much resources things would take. You know, if you just arbitrarily say, here's the model, here's how much data I'm training, here's the hardware I'm going to run it on. If you can predict how long it's going to take and other qualities, how much memory is very easy to predict, but if you can predict the necessary components, then the actual optimization is pretty straightforward. So by lifting the prediction, we're able to really accelerate things.
Cool. Any question from the audience about you know, from the perspective of technical contribution or technical questions? Anybody?
See, Stephen.
Stephen, please.
Hi, Stephen.
So Nick, very, very nice. I was not familiar with federated learning, so I quickly brought up to speed. I'm very happy about that. Just for some background, I'm a chip designer that designs in the IoT space. Oh. And so I'm always skeptical of models that, you know, model the hardware resources in terms of compute and communication and energy.
Sure, sure.
There's a famous quote by a gentleman named Box, you know, all models are wrong, some models are useful.
Yeah, I love that one.
So have you, so in my area, we have to validate our model. So we actually have to build a hardware test bed and compare it to the simulation and revise the simulation. Have you done any validation? Do you have any publications that show this is how the model compared to an actual hardware implementation?
So are you referring to the carbon footprint one, perhaps? Or...
Yeah, the energy, that's, by the way, I'm a complete believer in everything you said. I think this is a dead end, but I think it's actually many years out before we wean away from the data centers. Just like it took a long time to quit smoking and, you know, other things.
Yeah.
Wow. And the examples I would use would be more technical. You know, we tended to, so before Meta, you know, there was Second Life, and there was a bunch of technical examples where we realized, you know, this is going to be much harder to do. But if you could point to any publications that compare, you know, hardware implementations with the modeling, I'd be very interested in that, because I know the software that I use to do validation of IoT hardware has inaccuracies, and we're always working against those inaccuracies.
Yeah, so I think the first thing I would say is that in the area of like estimating carbon footprint, I think the level of accuracy that people want to see and is acceptable is like apples and oranges with what you're talking about. So in this sort of, I mean, almost sort of world scale of pollution, the amount of inaccuracy is sort of part and parcel of the game. You really want to get the sort of order of magnitudes right. And so I think these models that we developed are, you know, as good as conventional climate models that do, you know, the same models that they use to do centralized training and sort of model those ones. But they're obviously highly inaccurate at sort of the fine grained details. So, you know, these two papers here are the ones you could look at. I also take them with a grain of salt in the sense that they are driven by assumptions. And so then you kind of put in these assumptions, but when you look at the input of those assumptions, you know that it's going to be very hard for them to capture the full story. But so an example of that would be they coming up with carbon and energy consumptions of a wide area network. So, if I'm sending a bit over the cellular network, all the different bits that need to kind of be used in that case, that is really going to be a fairly noisy measurement. So that's what I would, this is a fairly high level talk. And so a more complete treatment of the material would have sort of mentioned that. It's good that you picked that up.
Thank you. Can I just also add, so I've been looking at the, the GitHub website for Flower.
Yeah.
And I'm not seeing a easy place to find journal publications. There's a lot of tutorials, there's a lot of how-to, but I'm looking for, where can I just pull all the references that you posted on this presentation. So whereas there in the chat, there was someone pointed out another federated machine learning system. And in 2 seconds, I got to the reference publication. So there is a difference between your GitHub site and the one that's posted in chat that you might take a look at.
Yeah, sure. I guess we're more, we want to enable people to use federated learning. And so I guess we're kind of like leaning a bit more toward people being able to put it together rather than being academically rigorous in the setting of the tool. If you go to my groups page, you can find the papers.
Oh, that's good. Okay, that's what I needed to know. Thank you. Yeah. Excellent. Thank you.
Thank you. But feel free to just forward me a email. I'm happy to sort of send them to you in a more digestible fashion.
Okay. Thanks.
Yeah.
Thanks, Stephen. I think we are kind of running out of time, I believe. I think I was told Nick has to leave pretty sharp, 12.
Yeah, I should need to go pretty soon.
Yep.
I think it's worth just answering this one last question because there was this question about FedML. I guess I don't want to kind of, I tried to put a bit of a message in this talk, a little bit of that there are other types of frameworks. And so I'm not claiming that Flower is the best for all situations. We're just trying to nail a certain use case. And that use case really is extensibility and simplicity of use. There are other frameworks out there that nail other types of scenarios, like PySIFT, for example, is a very well-known one. They do great work there. And I think the way that PySIFT sort of excels is that it has very broad support of a variety of privacy-enhancing technology. It is a bit of homomorphic encryption and so on. I would say each of these other frameworks out there, they're an important part of the ecosystem too. And so finally, one of the things that we are trying to do is bring these frameworks together. So recently we announced a partnership with Intel. Intel has a framework called OpenFL. It has exceptional control over, there's many exceptional things, but one thing that jumps to my mind is that it allows you to do really fine-grained control over access permissions. It also has great support for SGX, not surprisingly, but also has, thirdly, support for trusted hardware. And so we're in partnership with them to build interoperable components that would allow people from Flower to use those components and vice versa. And I think that is a very healthy way for things to evolve, whereby all tools need to have a certain leaning. And so we should try to strive for maybe a few more standards and then allow different components and different frameworks to work together. Like, for example, you should have federations of clients where you have OpenFL clients, you could have PySIFT clients, you could have a variety of other different clients working together in federations. That would be a healthy thing to strive for.
Thanks, Nick.
Yeah, sure.
I think it's a very inspirational for the talk. I think everybody, I believe, learned a lot from this talk. There's another question. I think, Lel, do you have a time to answer this question?
I think I can answer this question, then I should probably run. But
yeah,
but
I think let's make it as the last question. Okay.
Sure. This is a great question. I mean, we're familiar with this problem. Many people who just want to get going with FL, because FL is fundamentally a distributed system, there's a lot of other noisy stuff you have to do that's a pain in the butt. that you don't have to do with centralized training. One of those things is standing up a server. You have to stand up the server, you have to allow communications to occur and everything. And so we're looking into ways whereby people could, more easily just stand up something to get get an example system running. You could always run a simulation that wouldn't require you to set up a host server. You can do everything, do a simulation just on your device. But that's not always, the next step, you might want to stand up a server somewhere and so on. So we're looking into ways to make that more turnkey. But thanks for inviting me. It was great chatting. I really love the questions and so on.
Fantastic. So I think, when your startup gets more established, we are more than happy to invite you again to talk about more about the startup.
Sure. I'd love to. I'd love to tell you more about the kind of commercial applications and stuff and the products that we can build on top of it. But I think, it's always, for us, the most important thing is always going to be the open source and the community, to see what people can sort of really enabling people.
Fantastic. Thanks so much, Nick. I really appreciate that. Spend your time with us. So this concludes today's seminar, and I'll see you next time. Thank you. Thank you, everyone.
Thank you so much. Take care, everyone.
Thank you. Yep.